Everyone, in this lecture I'll take a topic of MSc Final paper 8th-b and I'll take the topic of terpenoids, and in continuation of my previous lecture today I'll discuss determination of the structure of terpenoids. First point in the determination of the structure is to determine the molecular formula of the terpenoid under consideration, and we take a pure specimen of the compound or the terpenoid and we determine its molecular formula by qualitative analysis, that is by elemental analysis and molecular weight determination. First step is done, that is the molecular formula. Then if the terpenoid under consideration is optically active, then we measure its optical rotation or the specific rotation, and this step is particularly useful if the terpenoid is optically active, as it helps in distinguishing between two or more possible isomers. That is, for example, we take limonene and carbone. One is dextrorotatory and the other is levorotatory, so we can distinguish between the two possible isomers. Third point is to determine the functional nature of oxygen. If the terpenoid under consideration contains oxygen atom, then we have to establish its functional nature, or we can say we determine the presence of the functional group present in the terpenoid, and the most common functional groups present in terpenoids are alcoholic group, aldehydic group, ketonic or ether group. So we test them by usual laboratory tests. For example, for aldehyde we can do the common laboratory test, that is to react it with 2,4-dinitrophenylhydrazine. Then we can say if it gives yellow PPT, then we can say it contains a carbonyl group. Then we decide whether it is ketonic or aldehydic. Now the next step is the presence of C-alkyl groups in terpenoids. The frequently present C-alkyl groups in terpenoids are number 1 C-methyl group, number 2 isopropyridine group, and number 3 is isopropynyl group. So we do specific tests to determine the presence of C-alkyl groups. First we take the C-methyl group. This is its presence is determined by Kuhn-Roth method. The terpenoid is oxidized with chromic acid when all the C-methyl groups are converted into acetic acid, which we estimate volumetrically, so we can detect as well as estimate the presence of C-methyl group. Second is isopropyridine group. It is detected and estimated by ozonolysis. When we ozonize it, we get acetone as the product. So the amount is estimated volumetrically, and thus the number of isopropyridine group is determined. Third is isopropynyl group. On similar treatment, that is on ozonolysis, the isopropynyl group gives formaldehyde. So we can check whether it is isopropyridine. If we get acetone, then it is isopropyridine group, and if we get formaldehyde on treatment with ozone, we can say that it is isopropynyl group. Now the next point is the carbon framework of the terpenoid, or we can say it is carbon skeleton of the terpenoid. Sometimes dehydrogenation of the terpenoid with sulfur, selenium, platinum or palladium gives well-known aromatic compounds, and thus we can judge the carbon skeleton of the molecule. This is particularly helpful for the cyclic terpenoids. Next point is the presence and the number of double bonds in the terpenoid. When the terpenoids are presence and number of double bonds can be determined by common olefinic reagents. For example, as we know, the addition reaction, the addition of hydrogen, the addition of halogens, addition of halogen acids and addition of peracids. This is particularly important. On addition of peracids, we get, as we know, we get epoxides and acid. And similarly with Tilden's reagent, that is nitrosyl chloride, we get the particular nitrosyl addition product and the nitrosyl chloride. So this reaction, that is the addition of Tilden's reagent, is particularly important because it helps us to distinguish the nature of carbon atoms bonded by the double bond. For example, if the two carbon atoms joined by a double bond are tertiary, if both the carbon atoms are tertiary, then we get a blue colored nitrosyl chloride, as we can see in this reaction. If we get a blue colored product, we can say that both the carbon atoms are tertiary in nature. And if one of the carbon atoms joined to a double bond is tertiary and the other is secondary, then we get a colorless nitrosyl chloride. As we can see in this reaction, first we get an addition product, and that addition product then in the second step isomerizes to give the oxime, which is colorless. So on addition of NO-sil Tilden's reagent, if we get a blue colored product, we can say that both the carbon atoms are tertiary in nature, and if we get a colorless oxime, then we can say one carbon atom is tertiary and the other is secondary in nature. Here we should remember one thing, that the addition of Tilden's reagent or NOCl takes place according to the Markovnikov's rule. What is Markovnikov's rule? The negative part, that is Cl, is added to the tertiary carbon atom, and the positive part, that is NO+, is added to the secondary carbon atom. Now we come to the number of rings present in the terpenoid. With the help of the number of up till now we have studied the presence and number of double bonds. We have established the functional nature of oxygen atoms, so we know the functional group present in the terpenoid molecule. Now with the help of these two, we take the help of this table given in this picture. With the help of this table, we can determine the number of rings present in the terpenoid molecule. First, we convert the terpenoid into a fully saturated hydrocarbon, and with the help of this table, we can ascertain the number of rings present in the terpenoid molecule. If the general formula of the fully saturated hydrocarbon corresponds to CnH2n plus 2, then the terpenoid is acyclic. If it corresponds to CnH2n, then monocyclic. CnH2n minus 2, then bicyclic. CnH2n minus 4, tricyclic. And if it corresponds to CnH2n minus 6, that means it is tetracyclic, and so on. So we can understand this with the help of a simple example. For example, if we find that the terpenoid has the molecular formula C10H16O and the number of double bonds is 2, the functional group is CHO group, and we now will convert into a fully saturated hydrocarbon. What we do is that it has 2 double bonds. Then we add 4 hydrogen atoms for 2 double bonds, and we'll add 2 hydrogen atoms for doubly bonded oxygen atom. Or in other words, we can say that the CHO group is reduced to CH3 group to convert into a fully saturated hydrocarbon. So we have total increment of how many atoms? We have total increments of 6 atoms, and we'll remove oxygen from its formula. So its fully saturated hydrocarbon will be C10H22. This formula corresponds to what? CnH2n plus 2. Now with the help of the table which we have seen in the previous slide, this corresponds to the general formula. CnH2n plus 2 means that it is acyclic terpenoid. So in this way we can determine the number of rings in the terpenoid molecule. That is all for this lecture. In the next lecture, we will see the physical aids in the determination of the structure of terpenoid. Physical aids mean with the help of spectroscopy, UV, IR, NMR, etc. How these are helpful in the determination of the structure of terpenoids. Thank you. Have a nice day.